So the next important type of questions are divisibility problems. So in this divisibility problems, let us look at some examples. But what needs to be remembered? Theory-wise, you need to remember that x power n minus a power n is always divisible by x minus a for any natural number power. X power n minus a power n is always divisible by x minus a, and x power n plus a power n will always be divisible by x plus a. So you can derive this using remainder theorem. So you would have remembered what remainder theorem is. So if this is a polynomial in x, if you put x is equal to a, you get a power n minus a power n. So p of a is always equal to 0 for whatever value of n. So x minus a is always a factor. Similarly, if you have x power n plus a power n, and if you put x is equal to minus a in this, p of minus a is minus a whole power n plus a power n. So if n is equal to odd, you get minus a power n plus a power n, which is equal to 0. So p of minus a is equal to 0 for all odd natural numbers, hence x plus a is a factor if n is an odd integer. So once you remember this, x power n minus a power n is always divisible by x minus a for all values of n, but x power n plus a power n will be divisible by x plus a for all odd natural numbers. So now let us see how we can use this in divisibility problems. So the first problem that we are going to discuss is, show that 1992 power 1998 minus 1955 power 1998 minus 1938 power 1998 plus 1901 whole power 1998. This expression, this number is divisible by 1998. We have to show this. So let us see how we can show this using these theorems. So now let us try to manipulate this so that I can apply this theorem. So I can see that all the powers are same, 1998. So now if I have something like x power n minus a power n, it will be divisible by x minus a. So first let me combine these two. So let us call this expression as p. So p is equal to 1992 power 1998 minus 1955 power 1998 minus of, so let me combine these two. So I have made this into one group, and minus of 1938 power 1998 minus 1901 whole power 1998. So this is of the form x power n minus a power n. So you can see that 1998 and 1998 are same. So x power n minus a power n. So this is divisible by 1992 minus 1955. 1992 minus 1955. So what is 1992 minus 55? 42 and 42 minus 5 is 37. So this group is divisible by 37. Similarly, minus, this is also of the form x power n minus a power n. So this will also be divisible by 1938 minus 1901. So which is equal to 37. So now this is also divisible by 37. This is also divisible by 37. So I can say that p effectively is divisible by 37. So now I have to prove that p is divisible by 1998. So I have proved that p is divisible by 37. Now what I do is, I'll group these terms in another way. So I'll group these two terms and these two terms together. So 1992 power 1998 minus 1938 power 1998 minus of 1955 power 1998 minus 1901 power 1998. So this is also equal to p. I have just rearranged the terms. So now this is also of the form x power n minus a power n. So this expression, this bracket, is divisible by 1992 minus 1938. that is equal to 54. That means this bracket is divisible by 54. And if you take the other bracket, this is also of the form x power n minus a power n. So this is divisible by 1955 minus 1901, that is equal to 54 again. 1955 minus 1901, which is equal to 54. So this bracket is also divisible by 54. This is also divisible by 54. Hence P is divisible by 54. So now what is the effective conclusion? P is divisible by 37 and also P is divisible by 54. P is divisible by 37 as well as 54. And you can see that. So P is divisible by 37 as well as 54, and GCD, greatest common divisor of 37 and 54, is equal to 1. There are no common factors between these two. Hence P is divisible by 37 into 54, which is equal to 1998. Hence P is divisible by 1998. So that's how we have shown that this total number, whatever this is divisible by 1998. So now let us look at another divisibility problem. So you have to prove that 2222 power 5555 plus 5555 power 2222 is divisible by 7. So we have already seen what you need to remember. We have to remember that x power n minus a power n is always divisible by x minus a for all natural numbers, and x power n plus a power n will always be divisible by x plus a for all n belongs to odd natural numbers. So x power n minus a power n is always divisible by x minus a for all natural numbers. X power n plus a power n is always divisible by x plus a for all odd natural numbers. This is the first thing that you have already remembered. Now let us see one more thing which you need to remember. So now x plus a whole power n, x plus a whole power n can always be written as some k times x plus a power n. So if you expand x plus a whole power n, you get c naught x power n plus c1 x power n minus 1 into a plus c2 x power n minus 2 times a square plus so on cn minus 1 x a power n minus 1 plus cn into a power n. So can you see that this term contains an x, this term contains an x, this term contains an x, that is all these terms till the penultimate term are divisible by x. So all these terms can be written as some k times x from here to here. And what is the thing that is remaining? Cn is 1 plus a power n. So all the terms from the first term to the penultimate term are divisible by x. So all of them combinedly can be written as some k times x, and the last term is a power n. Similarly, x minus a whole power n can be written as k times x plus a power n if n is even, or kx minus a power n if n is odd. So depending on whether n is even or odd respectively. Because we know that if you have x minus a power n, you will have an alternate plus minus sign. So if n is even, the last term will have a positive sign. If n is odd, the last term will have a negative sign. So if you can write this directly, it will be useful in problems. Now, if you have a special case where a is equal to 1, a power n will be equal to 1. So x plus 1 whole power n can be written as some kx plus 1. And x minus 1 whole power n can be written as kx plus 1 if n is even, and kx minus 1 if n is odd. So I hope you understand this theorem. So this is a very useful theorem in binomial theorem when you have divisibility with small numbers. Next, the other thing that you need to remember is, so let us take an example. If a number n is of the form 7k plus 3. So if a number is of the form 7k plus 3, then what is the remainder when n is divided by 3? So remainder when n is divided by 7 is 3. So if you have a number n as 7 times something plus 3, so the remainder will be 3. If you have a number something like 7k minus 3, then what is the remainder when n is divided by 7? Will it be equal to minus 3? No, because whenever we talk about remainder, we have to report positive remainders. So if a number n when divided by 7 leaves a remainder r, n has to be of the form 7k plus r. So if you have plus sign here, whatever is remaining is the remainder. But what happens if you have a minus 3? So you have to write it as 7k minus 3 minus 4 plus 4. So that is equal to 7 times k minus 7 plus 4, or 7 times k minus 1 plus 4. So 7 times something, you have plus 4. So the remainder will be plus 4. So if you have 7k plus something, exactly this will be the remainder. If you have 7k minus something, the complement of this with respect to 7 will be the remainder. That is 7 minus 3 will be the remainder. So you have to be careful. So if you have 7k plus 3 will be the remainder. 7k minus 3, the remainder is 4. So similarly, if you have 8k plus 2, so the remainder when this number is divided by 8 is 2. But if you have 8k minus 2, so what is the remainder when this number is divided by 8? It will be 8 minus 2, which is equal to 6. So if you remember all this, if you have understood all this, let us apply this and try to solve this problem.